Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here are links to online seminars and study manuals for exams P, FM, IFM, and LTAM that I offer. I direct the actuarial program at Illinois State University. Information about it can be found at smarturl.it/actuary. If you would like to offer a tax-deductible, to the extent allowed by law, donation to support our students, please go to smarturl.it/help-ISU actuary. Here's a problem for today for exam P. Let P be the probability that an MP3 player produced in a certain factory is defective, with P assumed a priori to have the uniform distribution on 0, 1. In a sample of 100 MP3 players, one is found to be defective. Based on this experience, determine the posterior expected value of P. Here's the solution. Let us write n for the number of defective items in a sample of 100. Then, for a given value of big P equal to P, n is a binomial with n equal to 100 and P being the probability of success in a single Bernoulli trial. Then f sub P of P, given that n is equal to 1, is, well, by definition, f sub Pn of P1 divided by f sub n of 1. And f sub n of 1, that's the value of the marginal distribution of n, which we can get by taking the integral from 0 to 1 of the joint distribution of p and n of p1 dp, so all possible values of p that correspond to the value of 1 for n. Then the top can be written as f sub p of p times f sub n of 1, given that p is equal to p. And the bottom can be written as the integral from 0 to 1 of f sub p of p times f sub n of 1, given that p is equal to p dp. That's because this is a way to write the joint distribution as the marginal distribution times the conditional distribution, straight from the definition of the conditional distribution. Of course, we just reversed the conditional one, so this is very much like the standard Bayes formula, but we use it for continuous distributions. This is also called the Bayesian approach for that reason. And then the top is equal to 1 times 100 choose 1 times p to the first times 1 minus p to the 99, because p is a priori assumed to be uniform on 0, 1. So the density is equal to 1. And the second expression is simply we have 100 Bernoulli trials and 1 success. And the probability of that is 100 choose 1 times p times 1 minus p to the power 99. And we write the same thing in that integral at the bottom. And so the top becomes p times 1 minus p to the 99. And the bottom becomes the integral from 0 to 1 of p times 1 minus p to the 99. Because 100 choose 1 is in both expressions, so it cancels out. Of course, 1 can be ignored, so this simplifies like that. And we note that the integral from 0 to 1 of p times 1 minus p to the 99 dp, we can do integration by parts and write u equal to p, then du is dp. And then if dv is 1 minus p to the 99 dp, then v is equal to minus 1 minus p to the 100 over 100. So this becomes minus p times 1 minus p to 100 over 100 evaluated from p equal to 0 to p equal to 1, minus minus, so plus the integral from 0 to 1 of 1 minus p to the 100 dp divided by 100. And the first expression is 0, and the second one we write as 1 over 100 times minus 1 minus p to the 101 divided by 101, which is the function whose derivative is 1 minus p to the 100. And then this expression is 0 at p equal to 1, and then we subtract the value at p equal to 0, and because we're subtracting and we have a minus in front of it, that those will cancel, become positive. So this whole thing will be 1 over 100 times 1 over 101, which is 1 over 10,100. And this means that f sub p of p, given that n is equal to 1, is equal to 10,100 times p times 1 minus p to the 99. And now we calculate the expected value of p given that n is equal to 1, which is what we want to find. And it's the integral from 0 to 1 of p times 10,100 p times 1 minus p to the 99 dp. That's 101 times the integral from 0 to 1 of p squared times 100 times 1 minus p to the 99th dp. And we do integration by parts and write u equals to p squared, so that du is 2p dp. And dv equals 100 times 1 minus p to the 99th dp, so that v is equal to minus 1 minus p to the 100. So this becomes minus 100 and 101 p squared times 1 minus p to the 100, the whole expression evaluated from p equal to 0 to p equal to 1, plus 2 times 101 will give us 202, so the integral from 0 to 1, 202 times p times 1 minus p to the 100 dp. And the first expression is 0, and we left with only with the second one, so it's 202 times the integral from 0 to 1 of p times 1 minus p to the 100th. And we do another integration by parts. We say u equals p, then du is dp, and dv is 1 minus p to the 100 dp, so that v is equal to minus 1 minus p to the 100 over 100. And this becomes 2, after evaluation of all these things, becomes the 2 times the integral from 0 to 1 of 1 minus p to the 101. Because 202 divided by 101 is 2. That's where 2 comes from. While the the product of uv evaluated from 0 to 1 will be 0, so that's why we ignore it. And now, what is that integral from 0 to 1 of 1 minus p to 101? We would know that the function whose derivative is this expression will be minus 1 minus p to the 102 divided by 102. And then when we evaluate it from 0 to 1, we would end up with 2 divided by 102, which is 1 divided by 51, which is what we were looking for. That's the answer. Actually, if you know this fact, that the posterior distribution of p in this case is beta with parameters 1 plus 1 equals 2 and 99 plus 1 equals 100, then its expected value is 2 over 100 plus 2, which is 1 over 51. We just calculated that. That's the same answer. So if you know this property of the beta distribution, which shows up as a posterior distribution in this case, then you're basically done. But that's not a required knowledge for this test, although knowledge of posterior distributions based on certain priors is something that shows up on the later exam. In any case, this is answer E. Please remember this is copyrighted material. This problem was created by me. All rights reserved. Reproduction in whole or in part without express written permission from the author is strictly prohibited.